Hello and welcome to the first video about QCD on the lattice at non-zero density. In this video we will start focusing on the basic theory of non-zero density QCD, in particular go from the continuum to the lattice like we did in the case of non-zero temperature, and we will discuss three important facts about non-zero density QCD, which happen to all be called problems, and these are the sign, the overlap, and the silver blaze problems. But let us start by simply stating that effect of non-vanishing quark number density are to be accounted for within the grand canonical description of our statistical system. For that, the partition function takes the following expression, where you can see the chemical potential that makes its appearance, and that is coupled to its conjugated quantity, which is the density, or the number operator, and then when you divide by the volume, it becomes the density. Now, when you want to consider non-zero quark chemical potential, that is an asymmetry with respect to how many particles rather than antiparticles you have in your system, this partition function is expressed as a function of mu q, and sometimes also in terms of mu b, which is 3 times mu q, and that then it's coupled to the baryon number operator rather than the quark number operator, which contains the same factor of 3 at the denominator. Okay, and we need to keep in mind in all this treatment in the grand canonical description that, for example, in the case of NF equal to the generate light quarks, we have conserved charges from global symmetries of the theory, such as the quark number density, defined as the sum of the densities of up and down quarks, and electrical charge density, which we call Q. That's a combination of the up and down density that takes into account the different charges of the constituents quarks, and the isospin number density, which is where instead you subtract the density of the down quarks, for example, from the density of the up quark. And to this correspond different setups for the chemical potentials as highlighted in this box. And the observables that we can then consider in a similar setup on top of what we already saw at finite temperature that can be generalized to the case of non-zero temperature and density are charge or quark number or densities, such as NQ, where its expectation value is given by a derivative with respect to the quark chemical potential of the logarithm of the partition function. As usual, small or capital letters are there to indicate densities rather than extensive quantities that corresponds to those densities. And we are also interested, and we will discuss about fluctuations of the conserved charges, which are a further derivative of the density with respect, again, to the corresponding chemical potential, in this example, the quark chemical potential. There are some facts about the phase diagram at non-zero chemical potential that we need to discuss in order to start getting a feeling about what is happening when we switch on a non-zero, for example, quark chemical potential. And one of these facts goes under the name of the silver blaze phenomenon. This is an intrinsically non-perturbative phenomenon, and you need to bear in mind that mu is nothing but the energy cost of adding the lightest particle coupling to mu to your system, and by coupling to mu I mean carrying the corresponding quantum numbers. And at zero temperature, the physics happens to be fully mu independent, so independent of the chemical potential, for as long as this chemical potential is small enough, in the sense that the free energy keeps taking precisely its vacuum value until mu is not large enough. There are is the same as saying that there are no excitations for mu smaller than the mass of the state it couples to. This sentence defines what is the critical value of mu, after which the physics at zero temperature starts being mu dependent. In particular, this critical mu corresponds to the state of the smallest energy per unit mu, and it is where we observe an onset of the density, of the number density, which becomes different from zero, and it is the location of a transition. In QCD at non-zero baryon chemical potential, the lightest particle which carries non-zero baryon number is the nucleon, and one observes the so-called nuclear liquid gas transition to nuclear matter at some value of the critical baryon chemical potential that I'm reporting on the slides. Similarly, in QCD at non-zero isospin chemical potential, the lightest particle that couples to that as non-zero isospin in this case is the pion. And what we observe is that as soon as the isospin chemical potential is half the mass of the pion, here which convention you use for introducing the chemical potential can or cannot give you this 1/2 factor over here, there is a transition to a BEC phase with pion condensation. And yeah, just a trivia about the name. This is called Silver Blaze after the Arthur Conan Doyle story, in which the curious incident of a dog doing nothing during the night has provided Holmes with an essential clue for solving its case. And you have the reference where this nomenclature or naming was proposed. So I think this is the right moment to remind you about the sign problem and what it is and how it affects our lattice QCD approach. So this you have seen already. We have NF mass degenerate fermion flavors psi and bosonic fields A, and yeah, this form for the fermionic part of the Lagrangian. Then we would like to write down the expectation value of a generic observable, and after we integrate out the fermionic fields, we have an NF power of the fermion determinant, which depends on the bosonic fields. And what we would like to do is to interpret this entire quantity as a probability distribution function, which means that it has to be something real and positive. Why do we want to do that? Because our strategy in lattice QCD is to stochastically estimate the integral through a discrete sum of the function values, of the integrand values. And this we want to do sampling more frequently at values of the abscisse or of the independent parameter, from which the integral receives the largest contribution. And for this, I add already this one-dimensional example where you can see that it is way more effective to measure the integral sampling in a strategic way rather than sampling completely at random. This goes under the name of importance sampling, and it can be summarized in this formula for the one-dimensional example, where you basically factorize the integrand in two pieces, which the choice of the two pieces is made based on the fact that you want this h of x to be as flat as possible, and then you use the p of x to sample the abscisse, and according to the Monte Carlo integration theorem, you can then approximate the full integral stochastically with an average of the samples of the integrand at values of the abscissa that are extracted or drawn randomly, but according to this probability distribution function. And important sampling we want to embed into a Markov chain Monte Carlo paradigm, because we know that Markovian processes, provided that we come up with an algorithm that satisfies detailed balance and at least the relaxed version of ergodicity, is ensured to equilibrate in a way that the states that are produced in the Markov chain are distributed according to the desired equilibrium probability distribution that can be exactly that object, provided that we have reasons to believe that it is real and positive. Because otherwise it is, again, not effective to stochastically estimate the integral, even in the very strategic way I have described to you, pretty much like when I tried to plot these two functions using the same number of snapshots or frames in my TIX LaTeX processor, and I got a very bad result. Okay. So let us discuss then again what are the conditions for that ensure that our setup with fermions is a sign problem-free setup. It is not displaying this bad behavior. We do have a sign problem-free setup whenever there is at the same time positivity and reality of the NF power of the fermionic determinant. And while positivity is something that we can ensure by just having an even number of mass-degenerate flavors for which the determinant is real, for reality we need to have a matrix P which is invertible and that has the property of providing us with the dagger of the Dirac operator onto after application on the original D slash with P and P minus 1. This was first noticed by Alford et al. In 1999. And it is a necessary and sufficient condition for reality. Note, though, that the sign problem, which is also known as the complex action problem, has nothing to do, as not something specific to do with the fact that we have a setup with fermions. In fact, it is truly caused by the complexity of the weight in our path integral formalism that appears in the expression for the expectation value of O, but for example, SGA is the Yang-Mills action, and there we know that e to the minus SGA is real and positive. You see it here. In general, though, it can also occur that we have a sign problem in bosonic theories. For example, if you change this term because you have a Yang-Mills action with a theory with a theta term, and then you have a sign problem even though there are no fermions around. Also, the sign problem is the principal obstruction that we encounter when we would like to do real-time Minkowskian simulation. It is exactly the sign problem that prevents us from doing that. And it is ubiquitous, the sign problem, in the sense that even beyond QCD, you can find out that the sign problem affects the study, for example, of systems of strongly correlated electrons, such as the Hubbard model or graphene. We can actually trace back reality to some important discrete symmetry of the continuum Dirac operator, now coming back to the sign problem in setups in which we have dynamical fermions that we want to simulate, for example, in the framework of QCD. This property this discrete symmetry is the gamma 5 hermiticity, which is defined by these equations. And if this holds for the relevant Dirac operator, there are consequences on the spectrum of that Dirac operator, and in particular on the corresponding determinant, which is made real by the fact that this condition is fulfilled, as one can easily prove. Let's see now, when does gamma 5 hermiticity hold, when does it break, or when does it get modified? It does hold for most lattice Dirac operators at mu b equal to 0. So far it was continuum language. Now I'm referring to the lattice Dirac operator, and I'm telling you that for most of them, for as long as you don't switch on the baryon chemical potential, you have gamma 5 hermiticity in place. And it also holds at non-zero imaginary baryon chemical potential. So whenever you have a mu b, which only has an imaginary part that's different from 0. Gamma 5 hermiticity, on the other hand, breaks at non-zero real baryon chemical potential, mu b different from 0, because in that case, a modified version of the gamma 5 hermiticity is fulfilled. Notice the change of sign in mu b and the star. And in that case, what one has for the determinant is that this relation is fulfilled, and gamma 5 hermiticity breaks. No reality of the determinant. Gamma 5 hermiticity can also be modified rather than breaking. And this is what happens in presence of a twisted mass or at non-zero isospin chemical potential in a way that we will see on the next slide. So basically, in that case, you can recover a Dirac operator whose determinant is real. This happens, for example, when you have two degenerate flavors and non-zero isospin chemical potential, because modified gamma 5 hermiticity in that case preserves reality and ensures that we have a sign problem-free setup. As soon as we work in the basis of the up and down flavors and we assign to the different flavors two different values of the chemical potential that are differing by a sign. So this is the full Dirac operator. You have on the diagonal the single flavor Dirac operator for which you know that gamma 5 hermiticity is broken. And nevertheless, since you have different signs of mu in the different blocks, you can obtain that the determinant is real and positive. Or if we want to phrase it in the language of the condition a la alpha that al, there exists a matrix P which is invertible that ensures that you can get d slash dagger out of P d slash P minus 1, and that P is the matrix I'm writing down here on the slides. So this is one example of when gamma 5 hermiticity is modified, but in a way that for the full Dirac operator, still reality and positivity are preserved. Okay, next thing to discuss is how do we implement a non-zero chemical potential on the lattice. And we, as a first step, try to get inspired from what the chemical potential is in a continuum language. Then our starting point is surely the conserved nether charge that corresponds to the continuum UV1 global symmetry, which is the relevant symmetry for the fermionic part of the action. For example, in the free case, this is the fermionic part of the action, and it can be proven to be invariant if the spinors transform in the following way, which is the UV1 global symmetry of this action. And we then can move on to writing down the corresponding conserved nether charge by the spatial volume of the integral of the zero component of the current, which is given by psi bar gamma mu psi. Okay, at that point, how do we come up with an expression for the corresponding Dirac operator at non-zero quark chemical potential? By coupling the quark number operator via the quark chemical potential as a new term in our fermionic part of the action, which in particular modifies the Dirac operator in the following way. So you see that there is this further term. And this further term results in a complex action, because the way that the quark chemical potential enters is like an imaginary component of an abelian vector field, as if it were I times A4. And this leads to breaking of the gamma 5 hermiticity. Now, why is the continuum inspired way of coupling the quark chemical potential to the quark number operator in the continuum not a good idea? Because one can show that it leads to the unphysical divergence of the energy density as calculated using lattice perturbation theory. In particular, one finds out this type of behavior for the energy density difference. And then this is not a proper discretization, and one has to come up with an alternative discretization that was proposed in 1983 by Asenfratz and Karsh. They basically wrote down the nether current for the lattice action explicitly. So starting from the action discretized in the lattice formalism, where we know that there are the hopping terms, so that it is expressed in terms of nearest neighbors terms, and that there is a sum over all sides in our lattice. So what would then be an ansatz? An ansatz would be to take the hopping part of the operator and multiply each of the two terms by a function of the chemical potential. That is then something we need to work out explicitly. And how do we work it out explicitly? By observing that there are some constraints that it must fulfill. First of which, that at mu equals 0, the original action should be recovered. And therefore, this expansion of f a mu nu in terms of a mu q should be starting with a 1. And then the second term should be linear in mu q, because this would then reproduce the density term. And last but not least, you want this property to be fulfilled in order to ensure time reflection invariance. Now, taking these constraints into account, the simplest form one can come up with is the following form. And then we have a recipe for implementing non-zero chemical potential on the lattice. And this recipe entails favoring forward hopping in time by this exponential factor, and simultaneously disfavoring the hopping which goes backward in time with the corresponding exponential factor that has a minus sign. And this ensures the correct coupling to the conserved lattice current and also a correct naive continuum limit. And the next aspect to cover is how do we actually implement chemical potential on the lattice in practice. We need to remember that the fermion determinant is, according to the hopping parameter expansion, for example, corresponds to the exponential of a sum over gauge invariant closed loops of link variables. Just any closed loop of link variables contributes in the hopping parameter expansion framework to the determinant of the fermionic operator. Then in that framework, are these loops mu dependent or mu independent is the question we should ask ourselves. And one can easily understand that only those loops that are wrapping around the t direction are actually mu dependent, because in that case, forward hopping for quarks that propagate along a loop that wraps around the t direction is favored by this exponential factor, and backward hopping, which is the word line of the anti-quark, analogous to what we just said about quarks, gets disfavored by the corresponding exponential factor with a minus sign. All other closed word lines are going to be mu q independent necessarily, because they will include as many forward hopping in times as backward ones they include. So this is one thing we need to keep in mind. And the second is that the mu q dependence can in fact be implemented simply as a boundary condition. And in order to clarify that, I prepared this one-dimensional sketch for the forward hopping, where in particular hopping from n tau minus 1 to n tau is considered, and then hopping across the boundary from n tau to 1. Okay? And here are the terms that appear correspondingly in the hopping part of the Dirac operator, to which we can apply a change of variables, both for psi and for psi bar, according to these expressions. And if we do that and we look at the transformed hopping terms, we find out that this hopping term from n tau minus 1 to n tau stays completely unchanged, as much as all other hopping terms, apart from the hopping across the boundary from n tau to 1, in which you obtain a factor. And this is exactly the way you want to implement the mu q dependence as a boundary condition, specifically by setting psi prime equal to minus this exponential times psi prime evaluated at 0 rather than at n tau. And you must make sure you don't forget the minus sign here, because this is what ensures that your fermionic degrees of freedom are statistically behaving as they should according to the Fermi statistics. And a natural question then that comes to mind is whether there is an easy way out of the complex action or sign problem, because one can think about the expression for a generic expectation value of any observable O, and one can think of re-expressing that integral in a way that the determinant is split into a modulus, which is real, and a phase. And then one can basically include only the modulus in the Boltzmann weight and let the phase in the observable part. Then what we would be measuring is the ratio of evaluations over the phase quenched ensemble, which is the ensemble in which you have only used the modulus of the determinant as a weight, of two different observables. At the numerator, the original observables times the phase, and at the denominator, you still have to divide by the expectation value for the phase. And while that sounds very reasonable, I must warn you that there is an important caveat to this approach, which comes in the form of an exponentially severe overlap problem, which is easily understood if you look at the expectation value of the phase over the phase quenched ensemble. And you work out the corresponding expression to be nothing but the ratio of the original partition function, the full partition function, by the phase quenched partition function, which in turn can be written as the exponential of minus delta F, the variation in the free energy, over the temperature. And since we know that free energy is an extensive quantity, we can rephrase that variation in terms of the variation of the corresponding density, which singles out a volume factor. And that's the beast we have to fight. Because then one remarks that Z is necessarily smaller or equal than Z phase quenched, due to the fact that in one case you are weighting by the modulus, which is always positive and real. And then we have good reasons to believe that the expectation value of the phase is going to be 0 in the thermodynamic limit due to this behavior. Then we understand that sampling with the wrong reweighting factor can be exponentially in the volume inefficient, and it only works decently as long as the differences between the full partition function and the phase quenched partition function are small enough. One last remark is that by using the square modulus of the determinant as a weight and neglecting the corresponding phase or imaginary part of the individual flavors, we are doing nothing but weighting with the product of the corresponding d slash evaluated at mu q with different signs. So this is precisely the weight factor through which we sample correctly an f equal to QCD, but at mu I different from 0. And this is the phase quenched sampling. One more slide about the connection between the sign problem and properties of the Dirac spectrum. Why is that important? Because we have already established at mu equals 0 that we can we can build a relation connecting the order parameter for chiral symmetry breaking, which is the chiral condensate, and the infrared limit of the imaginary spectral density of this slash. This was generalized, this connection, to the case of non-zero values of the imaginary chemical potential when these values are large enough, which was possible thanks to the fact that in this case, too, the fermionic determinant is real and positive. And one then obtains a direct relation between the spectral density of the complex Dirac spectrum, of the complex spectrum of the Dirac operator, and the BCS gap, which is what we later on will consider as a signature or a tool for finding out whether there is superconductivity in the corresponding phase diagram. However, when you go at baryon chemical potential different from zero, you don't have positivity of the fermionic determinant anymore. And a novel mechanism for chiral symmetry breaking was proposed by Osborne, Splitov, and Verbascot in 2005. In continuum language, the correspondence is the following. That we have a massless Dirac operator, which is non-Hermitian, to which corresponds naturally a complex spectrum. So the eigenvalues that used to be aligned along the imaginary axis spread away from the imaginary axis in the complex plane, and the discontinuity in the complex mass plane of the chiral condensate is this time connected to an oscillatory spectral density. This goes under the name of the OSV mechanism. And also silver blaze is something we should mention in this context, in the sense that what silver blaze means in terms of the Dirac spectrum is that the spectrum itself has a mu dependence that sort of cancels out in order to ensure that the physics is independent from mu at t equals 0 for as long as mu is lower than the critical values. And this mu dependence was found to cancel at the level also of the oscillating spectral density, and I'm quoting the two relevant papers also in this case. So we are at the summary of this first video about non-zero density, QCD, from a lattice perspective. We have discussed that the sign problem is truly a property of the Dirac operator, which is crucial for the correct description of the physics of systems that are characterized by a net imbalance of matter, charge, strangeness, and whatnot. And one thing I didn't tell you is why do we call it problem? But you might have guessed by now. So we call it problem just because of the fact that the complex action is obstructing lattice investigation. So from our point of view of lattice practitioners, this is really a problem because we cannot employ standard important sampling, standard Monte Carlo methods. There are, however, densities that one can afford, in particular in spin models or for some classes of Hamiltonian when one can employ cluster algorithms. Another density one can afford is the non-zero density in two-color QCD, which is QCD with the gauge group SU2 that has pseudo-real representations, and this is the key property that ensures reality and positivity, and then the viability of Monte Carlo techniques. And there are also densities that one can afford in QCD, so really in QCD rather than two-color or spin models. And these, which were mentioned in the course of the video, are non-zero isospin densities, where you have an imbalance between the densities of up and down quarks in a setup with two degenerate massive fermions that can be simulated, and we will discuss about that in the next, in a coming video. And also purely imaginary baryon chemical potential was mentioned, where we again have reality and positivity, and that is also a topic we will discuss. Small net baryon number is must be tackled with Monte Carlo combined with some more sophisticated tools, which we are also going to discuss, such as reweighting, Taylor expansion, or analytic continuation. And that's it for these videos, other than the further approaches for tackling the sign problem, which I wanted to mention, even though I'm not covering them in this class for lack of experience and lack of time. I still want to mention them, so you can Google them or find some literature reference in case you're interested. Starting from the canonical partition function, which is in a canonical ensemble set up at fixed baryon density. And then there is density of states, where basically you, the method revolves around this object, the density of states, that gives you the proportion of occupied states at each given energy and density. And there is complex Langevin, which is based on a complexification of the degrees of freedom in the theory, in the relevant theory. And then the Boltzmann weight is constructed as a solution of a stochastic process. This is also a very interesting topic that I unfortunately do not have time to cover. Also, thin balls are another approach which is based on complexification of the elementary degrees of freedom of the theory. And in that case, the expectation values are expressed as sum of integrals over manifolds that are attached to the critical points of the complexified theory. A rather non-trivial method, which is based on what I just said. Last but not least, I want to mention tensor networks, which is where you sort of base your description of the system on ansatz, which are good ones for the description of quantum many-body systems. This is also an approach that is intrinsically sign problem-free and that has been employed, but particularly in low-dimensional theories. Yeah, I need to be short on this, but you still have the names and some idea of what they are. And see you in the next video.